Oh, Hello. Hi, and welcome to the fourth week session of the Statistical Mechanics NPTEL course. My name is Parasar. I am a PhD student in physics at IISc. Uh, so uh, today we'll be discussing uh, some problems, mostly on probability distributions. Uh, so this first problem uh, we have something related to the Gibbs phase rule, and after that we have a bunch of problems on like I said on probability distributions. So yeah, let's start the discussion. So this question is about a thermodynamic system with three components. So there is a solvent which is called C, and two solutes A and B. So all in all, there are three components in this system, and we have to find the dimensionality of uh, various surfaces or manifolds. So let's just look at this first part, which is about the dimensionality of the parameter space, or the space in which the phase diagram is constructed. Okay, so this is the dimension of this question is asking about the dimension of uh, uh, so this is the parameter space in which we construct the phase diagram. Or this is uh, so let's try to list what quantities are there. Uh, so of course the pressure and the temperature of the system must be specified. So these are two variables, and these two are the same for all the components, uh, for thermal and uh, mechanical equilibrium to hold. All right, and what else? So we have we must specify the number of uh, molecules of A, of B, and of C. But like if you look at the intensive quantities, the concentration of A, or the fraction of molecules of A and the fraction of molecules of B, these are sufficient. So N is the total number of molecules. So it is enough to specify these two ratios. Then obviously the third one, the third ratio, this fraction is automatically determined by the sum of these two. So there are two independent concentrations uh, or um, two independent mole fractions or concentrations which are intensive quantities, and of course here we have two independent quantities. So all in all, just a second. Yeah, so we have four independent parameters to vary. So uh, which can be chosen to be P, T, and Ca and Cb. So these are the concentrations of the components A and B. So this is the answer to the first part of the question, and we can also try to understand this uh, in uh, a different way of counting, but it is ultimately the same thing. Uh, so we want to find the dimension of the parameter space, right? So at a generic point in the parameter space, we have only one phase. Generic point in parameter space. So if there are some coexistence lines or surfaces, those are special points, special points or lines or surfaces. So those are not generic. For a generic point in the parameter space, we have only one phase. So if you want to directly apply the Gibbs phase rule formula, so that corresponds to the number of phases being equal to 1. So let us just quickly revise this formula. So the number of independent the number of independent parameters you can vary when you have uh, the number of components to be R, and if you have m phases in coexistence, this is the number of independent degrees of freedom. So now if we want the dimension of the parameter space itself in which the phase diagram is constructed, so then like we discussed, generically, like at some point in the parameter space you have only one phase in coexistence, so that corresponds to m equal to 1. So when you put this here, you see it as r plus 1. So here we have three components A, B, C. So 3 plus 1, which is 4. All right. So let me see if there are any questions. Oh, sorry. Okay. Yeah. So we have a four-dimensional parameter space to construct the phase diagram. That is about the A part of the question. Moving on now, in the B part, we have to find the dimensionality of the region in which two phases coexist. So two phases coexist. So in this formula, m then becomes 2. So then the number of degrees of freedom will be then 3, since we have three components. so we have a three-dimensional manifold or region in which uh, uh, or two phases can coexist in a three-dimensional region. And similarly, when we if we want three phases to coexist, so that will bring down another degree of freedom. So that means m equal to 3. So that's r minus 1, which is 2. So for every when we increase the number of phases that coexist by 1, if we demand that one more phase should coexist, then that will bring another constraint, let's say in the form of another Gibbs-Duhem relation. So if you remember in the earlier sessions, we discussed in detail about the Gibbs-Duhem relation, how all the intensive variables are not independent of each other. There's a relation which or there's a condition which they have to satisfy, and they're related. So for every new phase, we'll have uh, uh, we'll have one less degree of freedom to vary, to stay in that coexistence regime. So yeah, this is what we are seeing here, what we're calculating. So, and coming to the final part of the question, it is about the maximum number of phases that can coexist in the system. So the least number of degrees of freedom you can have is 0. So you can have points in parameter space and nothing less than that. With n phases coexisting. So if n phases coexist on points, then there will not be generally any uh, uh, any place or any region in the phase diagram where n plus 1 or more phases can coexist. So points, they correspond to zero dimensional manifolds, or you cannot vary any parameters. They are so fine tuned that they occur only when all the parameters are fixed. Maybe there might be a few such points, but there is no freedom in varying any parameter continuously. So this will occur like we discussed at points. So to find n where such thing can happen, so we can just simply set this to 0. So r here is 3 components, so 3 plus 2 minus n. So we can have 5 phases coexisting in this system at a single point. Yeah, so that would be like a pentuple point or something, but it is possible to have pentuple points where 5 phases coexist in this system. That is the point of this question, finding um, uh, how many phases exist at points is the point of this question. So anyway, is there any question about any question or comment or anything about the problem we've discussed? Okay, all right. Yeah, so let's move on to the next set of questions, which are mostly on probability. Okay, so let's look at the second question. Um, so in each of these questions, uh, we are going to look at uh, uh, just a second. Sorry. Yeah, yeah. So from here on, like in each of these questions, we will look at one new probability distribution which is important and occurs in various contexts. So yeah, uh, let us look at this question. So there is a coin, of course, tossing which will result either in head or tails. So the probability of falling heads is p. So the probability of falling tails is 1 minus p. And consider this experiment uh, where the coin is tossed uh, until a head appears for the first time. So it is tossed until head appears, and the experiment is stopped after that. So uh, this is a random process, and uh, we can uh, we can define a random variable using this experiment, which is the let's say x. We call this x. That is the number of tosses, or the number of times the coin is tossed. Let me write it that way. So remember, once a head shows up, the experiment is stopped. So this is obviously a random variable. So it can take values 1, 2, 3, and so on. Uh, so the question is, what is the probability that this random variable x is equal to k? So k can be 1, 2, 3, and so on. Okay, so for such an event to occur, for this random variable x to be equal to k, we should have this situation. This is how uh, this is how it should go. So the kth time, so this is the uh, kth result or kth blank here. So the kth time we should get ahead, and after that we are going to stop the experiment. But all these previous tries should result in should result in tails, because the experiment like wouldn't have reached this stage if there were heads anywhere here. So the probability for this to happen, and note that this is the only way in which the random variable x can be k. This is the only way in which the random variable x is equal to k. So the probability for this is the probability for tails to show up k minus 1 times, which is 1 minus p whole to the k. Sorry, 1 minus p whole to the k minus 1. So here the probability is 1 minus p, and these coin tosses are independent, and the kth time we should get ahead, and the probability for that is p. So this is the probability that that the random variable x is k, or the number of coin tosses in this experiment is k. Okay, so or let us write pk is equal to pk is equal to p times 1 minus p whole to the k minus 1. So I'll try to write this a bit differently. Yeah, so this pk is the probability mass function. Little p is the parameter in this problem. Yeah, hope that is clear. Yeah, so this is called the it's called the geometric probability distribution. Okay, and we'll have to find various properties of this probability distribution. Yeah, let me sorry. Yeah, is there any question? Okay. Yeah, sorry. Yeah, so the mean, coming to the mean of the probability distribution, so mean is going to be sum over the outcomes with non-zero support, k from 1 to infinity, k times p of k, right? So which is sum from 1 to infinity, k times 1 minus p to the k minus 1. Yeah, or let me just write it like this. Yeah, so we have to do this series. So it's obviously it's a convergent series because yeah, like 1 minus p is between 0 and 1. So we can find this. I mean, we can find the answer to this series like this. So we can start with let me say alpha to the k. So this will be or okay, let us consider this 0 to infinity. It's going to be 1 by 1 minus alpha. Let me also okay, let me slightly change the index. I mean, just redefine the index so that yeah, so it's going to be k times 1 minus p whole to the k. Yeah, so the k equal to 0 term doesn't contribute anything anyway, so we can add it. What's this up? Yeah, so I think okay, yeah, so let's just keep it like this anyway. Yeah, we'll come to that. So this is the formula we need. So this is nothing but the geometric series. So alpha, or the magnitude of alpha is less than 1. So yeah, so this is equal to 1 over 1 minus alpha, and we can get to the kind of sum we want just by taking a derivative of this with respect to alpha. So when you take a derivative with respect to alpha, if you apply this on both sides, this is going to be k times alpha to the k minus 1, and on the right hand side we'd have 1 by 1 over 1 minus alpha whole square, 1 over 1 minus alpha whole square. Yeah, so we can just write this as k equal to 1 to infinity alpha to the k minus 1. Yeah, so this is the infinite series that we need in this expression. So alpha is just 1 minus p. If you compare these two, alpha is just 1 minus p. So the mean of this distribution would be p times 1 over 1 minus p whole squared, which is 1 over p. Sorry, yeah. So that is the mean of the distribution. And similarly, you can calculate the variance. Uh, yes, so we'd have to bring down another k in the sum end. So we can just take another derivative of this expression to get what we want. So starting with this, if you take a derivative with respect to alpha again, so that would give so what is here? Yeah, so it is k times k minus 1 times alpha to the k minus 2, and this will be equal to 2 by 1 minus alpha whole cube. Yeah, so we can find out what sum of k square alpha to the k minus 1 is from this. Yeah, so the k equal to 1 term doesn't do anything, so it doesn't contribute anything. So this is k from 2 to infinity, k square alpha to the k minus 2 minus anyway, let's so k equal to 2 to infinity k times alpha to the k minus 2 is this. Yeah, so from this we can find, since we know this already, we can find this. Yeah, so this is going to be sum over k equal to 1 to infinity k square times alpha to the k minus 1 divided by alpha. So this is what we want, uh, minus the k equal to 1 term, which is 1 over alpha, yeah. So the first term can be rewritten like this, just by adding and subtracting the k equal to 1 term. Yeah, so yes, and the second term we already know what that is. So that is 1 over alpha times k equal to 1 to infinity k alpha to the k minus 1 minus 1 over alpha. So yeah, since we have already written that, it will become minus 1. Let me check if everything is correct. Yeah, that looks fine. So this is equal to, this whole expression is equal to 2 over 1 minus alpha whole cube. So this is what we want. Let's call this S2. Yeah, this is what we want. Let's call this S2, and uh, this term we have already calculated, and that is 1 by 1 minus alpha whole square. Yeah, so finally what we have is alpha 1 over alpha S2 is 2 by 1 minus alpha cube plus yeah. So S2 is then let me just do it like this. So we have again a coin uh, whose probability of falling heads is B. This coin is tossed n times. So the random variable here is the let's call it x. X here is the number of times heads appears. So let me denote that this is n times. Number of times heads occurs or heads shows up. So we can look at for example one configuration in which this can happen. So so for example you can get heads like this k times or x times. So this is uh, the the random variable is x, and we have to find the probability that this is equal to k. So you can get heads let's say the first k times and tails the next n minus k times. This is one such one configuration in which this can happen. But of course this is not the only one. So to count the full um, sorry, first let us find the probability of this one particular configuration uh, uh, occurring. So the probability of this configuration is p times k. So the probability of each of these are independent. So these are independent events. So the probability of this one particular configuration is p to the k times 1 minus p whole to the n minus k. But of course there are many more configurations in which the random variable x is equal to k. So the number of such configurations is obviously the number of ways in which we can select k slots out of n. So it is n choose k. And the probability distribution finally is n choose k times p to the k times 1 minus p whole to the n minus k. This is called the binomial probability distribution. So we have to calculate the mean of this distribution. So first of all, before doing the calculation, uh, uh, we can see what, I mean, we can try to guess what the answer should be. So since uh, uh, these are all events which are independent, since the probability of falling heads is p, we naturally expect the number of heads to be p times n in the limit n going to infinity. So the naturally guess should be something like p times n. So let's see. I mean, we have to do some algebra, some calculation to uh, to get to this. Let's try to do that. The expectation value of x, the mean of this probability distribution is this. So that is going to be this. So it's going to be k minus 1 factorial here, the denominator, and yeah, so it's going to be p times 1 minus p. Let's bring out the factors of these. Okay, from 1 to infinity, n factorial by n minus k plus 1 factorial into, so we have to uh, compensate for this. uh, Sorry. Sorry, this is from this is from 1 to n. Sorry. So it's going to be p to the k, p to the k minus 1. We move it, try to move this. Yes, yeah. So it's going to be p to the k minus 1, 1 minus p whole to the k minus 1. And we have compensated for this by this term. Um, so we have, of course, we have a k minus 1 factorial here. All right, okay. Yeah. So this is going to be, let's leave it like this. Yeah, so let us put everything together. Yes, so we have just factored out pn1 minus p, and we also factored out an n here, so that is going to be, that's going to look like np times I'm very sorry. So here it is n minus k, sorry, this is also n minus k. Yeah, so we can keep this as n minus k actually, so no need to factor out 1 minus p, I'm sorry. Yeah, so yeah, just rechecking everything. Yes, yeah, that looks like that looks right. So this is going to be n minus 1 factorial p to the k minus 1, 1 minus p whole to the uh, yes, yeah, 1 minus p whole to the n minus k by divided by n minus k factorial times k minus 1 factorial. So we can redefine this this sum, the index, this variable in the sum, to write this as 0 to n minus 1, n minus, yeah, n minus 1 factorial p to the k 1 minus p whole to the n minus 1 minus k, yeah, divided by n minus 1 minus k whole factorial times k factorial. So this is nothing but 1 p plus 1 minus p whole to the n minus whole to the n minus 1, which is just 1. So finally we have np, which is what we guessed right at the outset. So yeah, just by doing some manipulations to the to the factorials, we can find this sum. Yeah, so similarly the variance involves taking the summation with the k square here. Yeah, so similarly we can bring down uh, we can rewrite this summons to reduce it to a sum over uh, uh, to reduce it to a binomial sum over uh, over these variables, one p and 1 minus p, but with different exponents, but the spirit is the same. Yeah, so in the interest of time, we'll just skip that, since we've already done one such calculation. uh, is there any question? Okay. Yeah, so let's move on to the next question. So let's look at uh, a particular limit of this binomial distribution. So so this binomial distribution models something where we have an event that can, let's say, take two possible outcomes happening many times. So it might be interesting to consider the case in which this number is taken to infinity, like the number of times the coin is tossed. When that is taken to infinity, uh, and the probability for heads showing up going to 0, such that their product is finite. So p times n is lambda, that is finite. uh, so let's find out what this probability distribution reduces to in this limit, or what does it uh, converge to in this limit. So this in this particular limit. So we can just directly look at the probability density, or the probability mass function. So that is going to be so p is going to be lambda by n. Yeah, sorry if my this capital P, like the big P and the little p, are looking the same. So yeah, this is the probability mass function. So P is lambda by n. So let us just express this in terms of the factorials, and uh, let's try to rewrite this. So it is going to be lambda to the k by n minus lambda whole to the n minus k. Yeah, actually, yeah, it will be uh, useful if we factor out a particular term. Let's see. So uh, yeah, so this is the probability mass function. Let me just write one more step. This is lambda to the k. Yeah, so far we have done nothing actually, just like rewritten this expression in this fashion to separate out the terms which depend on n. Yeah, so now take the limit n going to infinity of this expression. That is what we have to do. So let's look at the first factor. So that is going to be n times. So limit n going to, yeah, so we have to find this limit. So after cancelling some of these terms, we see that it is n times n minus 1 times n minus k plus 1 divided by so there are k such terms here. Yeah, there are k such terms, and this can be written like this: n minus lambda k times. So we are just looking at this first factor. So it's going to be n by n minus lambda times n minus 1 by n minus lambda dot dot n minus k plus 1 by n minus lambda. So for any finite k, yeah, so k is so first we have to take the limit n going to infinity. Then I mean for any finite k, we have like finite number of terms here. So we have k terms to be precise, and so we have finite number of terms, and for each of these the limit exists, like the limit n going to infinity. These expressions exist. So and each of these is equal to 1. So the limit for this full expression also exists. So we have finite terms, and each limit is 1. I mean each limit exists and is 1. So the limit n tends to infinity of this thing exists actually, this whole thing that exists and is equal to 1. So since this limit exists, we can now look at the second term. So that is a standard result. So the limit n going to infinity 1 minus lambda over n whole to the n, this exists and is e to the minus lambda. So since both of these limit exists, indeed this probability distribution function in the limit n tending to infinity, that will converge to this new probability distribution function. Let us write that. So limit n going to infinity p of k is e to the minus lambda to the k by k factorial. Yeah, so k can now take any positive natural number, or any positive integer. Let's move on to the next question, where we will calculate some properties of this distribution function. Yeah, so p of k is e to the minus lambda to the k by k factorial. So note that this e to the minus lambda is there, so that the probability mass function is properly normalized. So you can check that if you sum this to infinity, from 1 to infinity, obviously this will give e to the lambda. So this is a valid probability distribution. You can check that this is 1. Lambda, of course. and it can be any positive number. So yeah, so in this question we have to find the cumulants of this probability distribution. So how is a cumulant defined for a probability distribution? So cumulants are defined using the characteristic function. Characteristic function. Yeah, so and what is this characteristic function? So it's an alternative way of specifying the information about the probability distribution function. It's basically a Fourier transform of okay, let me use a different symbol, q. So the variable in terms of which phi is defined, or phi is a function with q as a variable. So let me put it that way. It is the expectation value of this object. Where this expectation value is calculated with respect to the probability distribution. Yeah, so let us calculate this expectation value to find the characteristic function. So the random variable x here is k. K is the index of the summation. Q is the variable of the characteristic function. So yeah, let us look at this summation. K is equal to 1 to infinity e to the minus lambda, and it is going to be yeah, of course, lambda times e to the iq whole to the k divided by k factorial. So this is nothing but e to the minus lambda times the summation. The summation is the this is equal to exponential of lambda e to the iq, or it is equal to exponential of lambda e to the iq minus lambda. Okay, all right. So uh, that is the characteristic function. And coming back to the definition of cumulants. So cumulants are defined using the logarithm of the characteristic function. So consider log phi of q. The cumulants are defined using this. So this thing is equal to yeah, this is how the cumulants are defined. So uh, so we can use the form of phi of q we got. So log phi of q in our case is for this particular probability distribution is lambda times e to the iq minus 1. So So we can yeah, sorry, okay, since this is the characteristic function, yeah, so we should have yeah, so there is this I here in the definition, because we have defined it as the exponential of iqx. uh, this will also have the corresponding definition. So yeah, so we can try to read out all the cumulants from let's say by doing a Taylor expansion of this around q equal to 0. So, so of course there would not be any constant term for any probability distribution, and this is going to be iq plus iq squared by 2 factorial plus iq whole cube divided by 3 factorial and so on. So the first cumulant, and indeed all the cumulants, are equal to lambda. So we can read off the coefficients here. All these coefficients are just 1 here. So there is a lambda in front. So all these cumulants are simply lambda. So Poisson distribution is characterized by this property that all these cumulants are equal, and yeah, I mean the Poisson distribution is such that the cumulants are all equal for all m. Okay, so so that is an example where we used first we calculated the characteristic function, and then uh, we have like read out the cumulants from that. So let me pause to see if there are any questions. Okay, yeah, so yeah, so let's move on to the next question. So in this question we are going to model the probability distribution of the lifetime of a light bulb using some drastic assumptions, but still it is it will be useful to see how we can think of trying to model various events. So so in this particular example, we are also going to see how the geometric distribution that we already saw, that will give rise to a continuous probability distribution. So anyway, let us first see what assumptions are underneath what we are going to do. So given any time, if you allow for some time interval delta t, so the probability that that this light bulb fails. So note that the bulb is just a placeholder, and this can be about any event that can occur, like success or failure. So we can replace the statement that the probability that the bulb fails to a statement that probability that something like some true or false event happens or something like that. So So the probability that the bulb fails in time in a time interval delta t, let's say it is delta p. So the rate at which the bulb can fail, this ratio, that is given to be mu, and it is constant. So this is the most important uh, assumption. So this is a constant, so it doesn't depend on time. So whether the bulb is like 10 years old or 1 year old, uh, this rate of failure is a constant, which is actually not a good assumption for actual practical bulbs, light bulbs, because they age, and uh, 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 let's say after 2 years of usage, they are more probable to fail in a given interval of time, uh, like because of all the history and all. But this is uh, I mean, like, in this assumption, that is not considered. So you can ask what are the situations in which such an assumption is valid and reasonable. So although it may not be practical for the case of light bulbs, the many cases, for example, like the radioactive decay of nuclei does definitely follow this pattern. Uh, so we'll see how uh, how the uh, how the like the lifetime of the bulb or a nucleus can be understood from this simple assumption. So like I said, this is not a very practical assumption for light bulbs because they age, but nevertheless there are situations or contexts in which this is a valid and reasonable assumption. So let me write that. So it's actually a valid assumption for radioactive decay. So what we can do is we can consider the probability for the bulb to fail uh, between some small interval t and t plus dt. Probability that it fails between times t and t plus dt. So we can try to think of this time interval as being made up of many smaller intervals. So in each of these small intervals, the bulb can either fail or not fail. It is very similar to this to the geometric probability distribution case that we considered in the very first question. Yeah, so we have two possible two possible outcomes in each of these intervals, and what we have to find is or what we're trying to find here is a probability that uh, the bulb fails between the times t and t plus dt. So that means it did not fail until time t. So it did not fail until time t. And the probability that we are asking is exactly the probability that we calculated in the first question uh, for uh, uh, for this coin tossing coin tossing problem. So when we think of these intervals, so divide just it's delta t. So divide the time interval t into intervals of delta t, and we want to take delta t to 0. So we want to make this very fine and take the limit when the time interval is very small. So the probability delta p that bulb fails in delta t time is actually mu times delta t, because we have because the rate of failure is mu, and we've already discussed about this point, that the rate is constant in this assumption. So this delta p, this probability is mu times delta t, and dp, which is the probability that it will fail exactly in this time interval between t and t plus delta t, that will be 1 minus delta p whole to the the number of intervals which is t by delta t times delta p. So this is going to be 1 minus mu delta t times t by delta t times mu delta t. So naturally we want to take the limit delta t going to 0, and clearly this limit exists, or at least so this first particular this particular factor limit exists and is a non-zero. So in that limit dp is going to be mu times e to the minus mu t times delta t. So if x is a random variable which is the exact time at which the bulb fails, this if it is this random variable, of course then for any particular value of x the probability is 0, because it can take a continuum of values. But we can define a probability distribution for this random variable x. It's a continuous probability distribution. And what we calculated just now, the probability that the bulb dies or fails between t and t plus delta t, that is exactly equal to the probability that this x is between t and t plus delta t. So what we calculated, this mu times e to the minus t, this is the probability that x is less than t plus delta t is greater than t. Yeah, so the we can, from this we can read off that the probability distribution rho of t, let's say, is mu times e to the minus e times e to the minus mu t. So this is the continuous probability distribution for x. So probability density for the random variable x. X is the time at which the bulb will fail. Alright, so this is called the exponential distribution. Okay, and like we're almost there. What we have to find is the probability that the bulb lasts for at least the time t. So it should not die, or the bulb should not fail before time t. So the probability that bulb lasts at least time t. So if you look at this probability distribution, it looks like this. It decays exponentially. Okay, let me use a different variable here, t naught. So what the probability that we want is this integral from t naught to infinity. So what we want is yeah, what we want is t naught to infinity right, which is going to be e to the minus mu t naught. Yeah, so this is a probability that the bulb lasts at least for time t naught. Yeah, so of course this decays exponentially with t naught. So of course, like longer the t naught, the lesser the probability is. So that makes sense, and it the probability decreases with t naught. I mean, yeah, the probability decreases exponentially with t naught. And this probability distribution function that we found for the time at which the bulb fails, that is called the exponential distribution for obvious reasons. So it has support for t positive, and for t less than 0 it is 0. So that is the definition of the exponential probability distribution. So yeah, so with this crucial assumption about the failure rate being constant in time and not being dependent on history, we've derived the probability distribution for the failure time. Okay, so we can say that like this geometric probability distribution, which is a discrete probability distribution, has its analog in the continuum probability distribution in the form of this exponential distribution. Okay, so that is about this question. Okay, so let's see. Yeah, so let us try to find some properties of this exponential distribution, in particular the cumulants. Sorry. yeah, the story is similar. We can find the cumulants uh, from the characteristic function phi of q is expectation value of e to the I qx. So that is going to be integral 0 to infinity yeah. So here it is important to okay, sorry, I think so this should be mu actually. Yeah, the coefficient that appears here for normalization, obviously that should be equal to this coefficient in exponential. So lambda is mu. So let me rewrite this. This is actually mu times e to the, that's a typo, sorry, mu times e to the minus mu x. So mu has to be positive for this to be a probability distribution. So it is equal to this, and since mu is positive, this integral is convergent, and that is going to be equal to 1 by iq minus mu. It's going to be 1 by mu minus iq. Yeah, so this is the yeah, so we have discrete probability distribution uh, with support on endpoints. So that means endpoints at which the probability is non-zero. So for this probability distribution, so for like out of all such probability distributions with support on endpoints, which probability distribution has the maximum entropy, and what is that entropy? Right, so entropy of a probability distribution, as you know, is defined like this. So we can yeah, we can try to guess what the answer is first of all. I mean, like you might have already heard about this or already know the answer. So roughly the entropy of a probability distribution tells you uh, how uh, how random the given probability distribution is. If the probability distribution is highly skewed to favor one particular outcome, then then we can say that the entropy is less crudely comparatively to the case when the probability distribution is not so skewed so that all outcomes are equally or all outcomes are similarly probable. So from this we can guess that if all the probabilities are equal, so that no particular outcome is favored compared to the other outcome, we might expect that the entropy is maximum, and that is indeed the case. Maximum when pi are all equal to 1 by n, and in this case the entropy would be log n, ln n, and this guess in fact is correct, and let us try to prove that. So we are going to like time permitting, we're going to try to do this in two ways, two methods. So the first method, we're going to use like the monotonic property of certain functions. So let's just try to calculate this quantity, this entropy minus log n. So we want to show that this is negative. So this is going to be sum over I pi ln minus pi ln pi minus log n. So you can write this as sum over I pi log 1 over pi plus sum over I pi log 1 over n. Yeah, so this is just one, so there's no harm in uh, doing an insertion of this. So it's going to be pi log of 1 by n pi. Yeah, so our goal is to show that this is always negative or 0. I mean, goal is to show that this is non-positive. Yeah, non-positive. So let us use nice property to consider this function log ln x. So I'm just trying to plot this. So it looks like this roughly. And let us also consider this function x minus 1. So the graph for this function must of course pass through this point x equal to 1 on the x-axis, but it is also tangent to this graph at x equal to 1, since log 1 is since the derivative of log function at 1 is 1. So this is x minus 1. Yeah, that doesn't look like a straight line, but yeah, hope that is clear. So we have this property that ln x is always less than or equal to x minus 1. So we can use this here in the expression we got. Sorry, s minus ln n then should be less than sum over I pi times 1 by npi minus 1, which is which is equal to 0. Yeah, so we have shown that the entropy must be always less than ln. Just a small point, just small correction here. So this summation is over only those values with non-zero probabilities. So this I should be in the support of this probability mass function. So if there are any piece if there are any i's with pi being 0, those do not contribute to this summation, this entropy, because limit p going to 0 from the positive side, p ln p is 0. So we may just drop these terms, or you can assume that this is the definition of entropy. Sorry, you can assume that the definition of entropy is such that the summation is defined only on those values with support in, with finite support in the probability mass function. Yeah, so anyway, so this thing is going to be, this right hand side here in this line in this equation is 0, because even for this even for this summation, the probabilities will of course have to add up to 1. Yeah, so we have shown that the entropy cannot be more than ln n, and it can be equal to ln n only when each of these only when 1 by npi is equal to 1. So from this property, log x, I mean log x to the base e is equal to x minus 1 only at x equal to 1. So for this to be an equality, all these 1 by n pi's, they have to be 1, or only when pi is 1 by n, if it's a uniform probability distribution. So our guess indeed was right, I mean our intuition, that the entropy is maximum when no outcome is skewed or favored. I mean when no outcome is favored, or the probability distribution is not skewed towards any particular outcome. So indeed the maximum entropy is ln n, and it occurs when the distribution is uniform. So let us actually look at another method to get to this, which will be very useful in physics, in statistical mechanics. So it's time. Yeah. Okay. So uh, we can state this problem like as follows. So to maximize S is equal to sum over I pi ln pi, subject to the condition that sum over I pi is 1. So all these variables are, all these probabilities are not independent. So we can think of these as some variables on which this function s depends. Right. So so this is now a problem of finding extremum in this multi-dimensional space, subject to this condition, which is a constraint, or so this defines a surface for you. This is finding extremum with respect finding extremum uh, subject to constraints in multivariables. Yeah, so let us say if we have some function f of variables x1 to xn, the constraint is g of x1 to xn is 0. Let us say this is a constraint. So it defines a surface for you in this n-dimensional space, and we have to find stationary points of this function on this surface. So schematically, so this is a full uh, space of n dimensions, and this is a constraint surface. G is defined by G is equal to 0. So stationary points mean that this variation of f, the function, must be 0. Let me say stationary point. Df is 0. So df can be written as dou by dou xi times dxi. So when there is no constraint, all these dxi's are independent, and for the variation to be 0, each of these coefficients individually have to be 0, which says that the gradient is 0. So that is the extremum condition for a function in the full space. But now we have a constraint, so these dxi are all not independent. So if you have only one constraint, only n minus 1 of them are independent. So so on this surface G is always 0 anyway, so this is an identity. dg, what we're going to write, what we're writing now is an identity. It's an identity on the surface. Or that means this quantity is 0. So we can see there is a relation between the various dxi's. So like we said, all the dxi's are not independent because of the constraint, and we can clearly see that from this expression. There's an identity, so all these dxi's are not independent. So what we can try to do is we can try to eliminate one of these so that we'd have n minus 1 independent variations. So there's a very nice trick, a very nice method to do this. It's called the method of Lagrange multipliers. So the process goes as follows. So find some lambda, such that uh, dou f by dou x, let's say xn, dxn plus lambda times dou g by dou xn times dxn is 0. So if you can find one such lambda, we can add the first equation to the second equation multiplied by lambda to get rid of this variable or this to get rid of this variation dxn. So then df plus lambda dg would be sum over k is equal to 1 to n minus 1 yeah, that's it, because the k equal to n term would have vanished because we have chosen lambda such that it happens, right? So now all these yeah, let me write it like this: dg by dxk dxk. So now all these variations are independent, and that means that we can set each of these coefficients to 0. So del f or df by dxk plus lambda, this is 0 for k equal to 1 to n minus 1 at a stationary point at extremum. Extremum or any stationary point in general. So but we constructed lambda, or we have chosen lambda such that this is 0. So ultimately yeah, so we have to find a lambda such that this equation is satisfied, and then we can use that lambda to eliminate one of the independent variations and find conditions for the extremum. So ultimately what it means is, so look, both of these conditions are ultimately of the same form. So if you can solve for these set of equations for some lambda, we would have found the extremum. Sorry. So if you can solve for these to find the extremum. Yeah, so this is a general method of the Lagrange multipliers. So we can quickly apply this to our problem. So in our case, f, the function to minimize is the entropy, and the constraint is just the fact that all the probabilities must add up to 1. So in our case, s is minus sum over pi log pi minus that's it, and g, so this is f, and g is nothing but sum over I pi. Let's say minus 1. Yeah, it doesn't matter, but yeah. So these are the functions we have. So quickly we can see that the condition should be dou s by dou pi plus lambda times dou g by dou pi is 1 is 0. So dou s by dou pi would be minus pi times 1 over pi plus log pi, and this thing is just lambda. So ultimately what we have is lambda is equal to 1 plus log pi, or pi is equal to e to the lambda minus 1. So it is independent of I. So all the probabilities are equal. So this is the solution for extremum. So since the probabilities must add up to 1, this must be 1 over I for maximum entropy. Yeah, so of course we again find the same answer, the same conclusion, but it's useful to do it this way as well, to use this method as well. So let's yeah, let's stop for today since it is already 8 o'clock. Yeah, so to summarize this last problem, we have found that the uniform probability distribution is the one that maximizes entropy uh, uh, with of course with no other constraint. Uh, so and we saw that like in two different ways. Uh, uh, so yeah, so and this finding does agree with this intuitive guess that this must occur at uniform probability distribution. Yeah, so that's all for today. So let's continue these discussions next week. Okay, see you. Thank you. Bye.